welcome back to the Infodump, the series where I do a deep but not necessarily scholarly dive into a particular topic. This time we are continuing once again with our current topic of physics, and last time we touched a little bit on the Renaissance and how it laid the groundwork for the scientific revolution and the ensuing Enlightenment. But before we get into anything about that, I've switched recording softwares to OBS, and my GPUs seem to be really weird about that, so I can officially say that some stuff is up. And so I am recording this at around 2:15 in the morning. So I'm recording this about 7.5 hours before it'll premiere. So if I come across super tired, super exhausted, all that stuff, that is why. I am up very, very late just trying to get this done, get this working, get this all sorted. I'm also coming off of a session of Reason to Live. If you're watching the video, there's an info card up in the top right to that series, but I'm coming off of recording an episode of that ran about an hour longer than usual. So that was fun. I mean, it was fun, but the extra hour obviously means that my timetable got shifted a lot. So, right. That's announcements and explanations out of the way. Let's dive into the actual topic of this little episode. So, like I said to start us off, last week we talked about the Renaissance, and this time we are going to talk about basically the immediate aftermath. So, as I said quite a bit during that episode, the Renaissance was really more a rediscovery, in Europe at least, of the humanities, of the arts, and to a lesser extent of the sciences. Of course, those sciences did still come back, but not to the same degree. You did, of course, have a lot of rediscovery of that stuff, but it didn't really take the foreground until the Enlightenment and the scientific revolution. Of course, there were, because time is always a bit of a blurry subject, trying to specifically delineate, this is when this started, this is when that started. It's best to think of the Renaissance and the Enlightenment and the scientific revolution as three largely overlapping periods of time. So you have the Renaissance, and about a third of the way through that, you start getting the beginnings of the scientific revolution. And about halfway through that, you get the beginnings of the Enlightenment, but we're still about a quarter of the way out from the end of the Renaissance. So it's all this sort of very blurred and mixed together time period. Unlike stuff like the Industrial Revolution a couple centuries later, where you can say, yep, this is the definitive thing that sparked a whole bunch of change everywhere. It's not so easy. It's a matter of looking at the whole system and saying, okay, well, these changes were happening in these places at this time, but they were still fairly niche, so do we say that it started when those early, sort of early adopters were experiencing this development, or do we say it started when the greatest number at once were adopting the development, or do we say it started once the majority of countries in the region had adopted the development, or once every country in the region had adopted the development? Like, it's this very tricky thing to try and nail down super hard, which is why I'm not really going to bother. I'm not going to give you, a definitive, this is when the scientific revolution was, this is when the Enlightenment was. No, that's not what I'm doing here. What I am doing is trying to explain for you folks what exactly the Enlightenment and the scientific revolution were. So, one of the places that you can say these things started was, of course, with Galileo, with Copernicus, and they certainly helped lay the groundwork for it. I would say that Galileo was sort of one of the early figures of the scientific revolution. Of course, there was also everybody's buddy, Newton. Newton is, of course, very famous, even among elementary school students, as the guy who figured out how gravity works. Well, not exactly how it works, but the math of what its effects are. People often paraphrase that as he discovered gravity. No. People knew about gravity for a very long time, because gravity is something you will realize exists if you so much as try to get up in the morning. It's not exactly fucking hard to figure out that the Earth is pulling you down. Now, it is certainly true that everyone largely took it for granted. It was just how things were. That's it. Nothing special about it. It's just how the world works. Newton, though, he had the insight of applying gravity, as in the thing that pulls us down, to help explain the mechanics of the Copernican model. And why, the planets take the paths that they do. Why stuff looks the way it does from our perspective. So, Newton was one of the first, if not the first, to really apply the idea of gravity to things beyond just the here and now. And this is sort of, a trend in physics. Physics in particular, but science in general as well, to a lesser degree. As we develop a better and better understanding of physics, we have to leave more and more of what we can see directly around us behind. Whether it's because we're operating on just an incredibly different scale, as is the case with quantum mechanics or astrophysics, or if it's because what we see on the day-to-day is just not entirely accurate on, say, a more subtle and precise level. Think of it a bit like rounding error. Actually, it's very much like rounding error. When you're dealing, to use the example from earlier, when you're dealing with astrophysics, missing a few hundred miles here and there means absolutely nothing. In your day-to-day life, miscalculating by a few hundred miles means you probably end up, if not on the wrong continent, then at least on the wrong part of the continent. Whereas if you are dealing with, say, quantum physics, missing by 100 miles means that you're not actually doing the experiment, you're just off having a vacation or something. Now, if we invert that and we say, okay, in quantum mechanics, you need to be able to pay attention to minuscule amounts of not necessarily space, but of information. The tiniest, subtlest change. Using the most sensitive instruments. That's how you get your information. But if you look at stuff in your day-to-day life, if you try to use that sort of approach, you'll end up finding that it doesn't matter if you're looking on such a small scale, because it's the difference between something that has, for our purposes, functionally the same effect, and something that has, for our purposes, functionally the same effect. It's just, it's the same thing on our scale, because we can basically just round out the difference. And, if you're doing astrophysics and trying to get the precision that you need for quantum mechanics, that's just not going to happen, because it's physically impossible to gain such precise data about such a large section of the universe. Because in order to, get all of that information, you have to have relatively low resolution. And I don't just mean like, zooming out on a camera, so the resolution, like the pixels or whatnot on a digital camera are lower. I mean, it's the same basic idea, but it's essentially in order to capture more information, or rather information about more things, without having the ability to capture more information in total, you therefore have to capture less information about each thing. So, tangent aside, Newton was one of the pioneers in realizing that we would have to leave the comfortable, notions about the measurements and such that we use in our day-to-day life behind us. He did math with numbers that are on a much greater scale than most people would really ever have to even think of, let alone work with. And of course, that included, gravity. He figured out gravity mostly just as a way of trying to understand the movements of the stars and planets. Newton was a very damaged and troubled person. I'm not going to try and psychoanalyze a man who's been dead for centuries, because I can't exactly talk to him, but he definitely had some issues. I don't know what it is with people who are math geniuses and also very religious, trying to calculate from hints and clues in the Bible or whatnot the exact date of the end times. But it's a recurring theme. Newton was one of those people. He was trying to precisely calculate, stellar and solar cycles and planetary orbits so that he could use that as sort of a map, if you will, a temporal map, to calculate the day the world would end. Which is a very interesting thing to think of, especially when you consider that all of his work was initially meant to be private, even though he was, essentially a professor or, researcher, really, at the time. He had to be basically manhandled into getting all of his information done and sharing it. That is why, even though there is a very credible claim, Leibniz very much made a credible claim to having developed calculus as we know it at roughly the same time as Newton. However, the issue there is, we know for a fact that Newton was basically sitting on all his notes and research for years. So we generally go with the claim that Newton figured it out first. Leibniz happened to figure it out a little bit later, still before Newton had published any of his research. So, two very smart people coming to roughly the same conclusions, a little bit of differences there in their exact methodology, but broadly the same conclusions. And that brings us to the whole, mathematical fight between people who support Leibniz, people who support Newton. Obviously, I'm in the Newton camp because, again, I believe it's more likely that this man had just been sitting on his research for long enough that someone else who was, just as smart and was living at the same time and had access to the same broad sorts of resources figured out the same thing. When you look at it from a probabilistic perspective, that's very likely. With Newton, we really start getting into the point where physics and math become very, very close-knit for a long time. Because Newton was doing all this math in order to understand physics. Unlike the approach that the ancient Greeks, for instance, had taken, where physics was really just the framework they used to explain the math. Which really makes some sense when you think about the fact that they were working from, very, compared to us, primitive level of technology and primitive level of understanding. But, well, that's the thing. Newton was also working from a very, very rudimentary framework. And the Newtonian laws of motion, for instance, are not at all what we would consider accurate to a precise degree today, but they are good enough that on a macroscopic scale, they are entirely accurate. Again, back to that whole thing about rounding errors. So, everyone knows about E equals mc squared. That is not exactly the equation. That is the equation for an object at rest. Once the object is no longer at rest, it becomes a much more complicated equation. And we'll get into that later, but it's called essentially the relativistic kinetic energy equation. And that simplifies at speeds that are a negligible fraction of the speed of light into one of Newton's laws. Kinetic energy equals 1/2 mass times velocity squared. It's just a simplification at negligible fractions of the speed of light of relativistic velocity equations. And so we use it. It's technically not accurate, but the inaccuracy is so many decimal points away from what we care about that we don't really care. We can say, okay, yeah, we could do this hard, long, complicated part, or we could do the short, quick, easy, and fairly accurate way that doesn't actually get us any more difficulties. Obviously, if you overuse that, if you overdo it, it will get you some minor inaccuracies. But generally speaking, we're not working on big enough scales to have to worry about that. So that really is where Newton started to become a foundation of modern physics. He created the laws of motion, or rather coined the laws of motion, which are actually still accurate to this day, with some degree of relativistic shenanigans going on. For instance, good old force equals mass times acceleration squared, force equals mass times acceleration. Using calculus, that is just the derivative of kinetic energy equals mass times velocity, or 1/2 mass times velocity squared. So if the original 1/2 mass times velocity squared isn't exactly right, obviously neither is the mass times acceleration. They're close, but not quite right. Similarly, if you try to make any sort of high-level math work with it, unless you're dealing with it on near light speeds, you're fine. It's not going to be a problem. If you're working on very, small scales, it's probably going to be a bit of an issue, just because you need all those decimal points. And if you're dealing with stuff moving really, really fast, yeah, that's where the relativity shenanigans come in and fuck everything up. But those other laws, that an object at rest will stay at rest until acted upon by an outside force, and that an object in motion will remain in that motion specifically unless acted upon by an outside force, those are both entirely correct. And you might be thinking, if you have, a sort of rudimentary, incomplete understanding of relativity and space-time, well, hold on, I thought gravity was just sort of deformations in space-time. That would be something being moved not by an external force, but by just gravity, which isn't really a force. And the answer to that is gravity might be a force. We're not really sure. We think we've picked up gravitons and gravity waves, but maybe those are just sort of like ripples in space-time. And we can't really know for an absolute fact because gravity waves would look a whole lot like just ripples in space-time. But what we do know for a fact is that what gravity does is make it so that a path straight forward in space-time is a curved path in space. So, really, once you factor in space-time, the Newtonian laws still hold there. An object still does not change its motion unless acted upon by an outside force. Even when there's gravity involved, it's still traveling in space-time along its same linear trajectory. The trajectory is just not linear in space, because time. So, that should help you understand a little bit why Newton is such a big deal, because those are hard laws of physics that he codified, and he had math to back it up, and he had experiments that proved the math. He was the guy who put every piece we've worked on so far together. Aristotle had the math and the explanations, but not the experiments, and so he was wrong a lot of the time. Galileo had the experiments and the explanations, but didn't really have any of the math yet. He did some amount of, minor math, but nowhere near the level that Newton ended up doing. And of course, there's also our boy Archimedes, who had the math and the experiments, but as far as we know, he didn't have... he certainly had quite a few principles and theorems to his name, but they were mostly just the result of that mixing of math and experimentation. Stuff like, the, hydrophysics, essentially. Buoyancy and all that. That was stuff that he had figured out through experimentation and laws. It wasn't... or experimentation and math. It wasn't so much that he had created some sort of universal principle, rather he figured out the math and did experiments and was like, oh, okay, this is how it works. Newton put all of that together. He put math, principles, and experimentation together in one. So he would have an idea, find math that reinforced it, do experiments that confirmed his predictions. Or, on a few occasions disproved them, but most of those occasions involved copious amounts of, shall we say, psychoactive substances in an attempt to discover the color indigo. That did not exactly work, and he also almost went blind from staring into prisms filtering sunlight. So, yeah. But even with his shortcomings, he was still one of the people who gave rise to modern physics and modern science. And I think, at least, he is probably the most significant person that we have talked about thus far. Yeah, even compared to Galileo. Because he fundamentally established what we now consider standard scientific practices, particularly in the realm of physics. And he was actually one of the most significant members of the Royal Society of London, which was essentially the first scientific, well, governmental agency, if you will. It's also one of the places where the word science came to be used in place of natural philosophy, although that was a little while later. And, well, sure, he was pretty petty as a member of the Royal Society. His famous quote about, "If I have seen farther, it is by standing on the shoulders of giants." Yeah, that was actually a dig at the famously short, I believe it was chairman of the Royal Society, who was a significant rival of Newton's. So even his most, inspirational and famous quotes are basically just snide, petty remarks. Which goes a whole lot to explaining how he could be so well-loved by posterity and so hated by his contemporaries. He was not a very popular man. But, as I said, he is one of the people who created modern science and modern conceptions of science. And for that, I think he has very much earned this episode on the Infodump. And with that said, I think it's about time I wrap this up, get this edited, get this uploaded, and then finally get some sweet, sweet sleep. So, thank you very much for listening, and I will see you next time.